All right. Hello, everyone. My name is Sam. I'm the CTO of Anapaya. Very happy to be here. Tim invited me. I'm probably a bit far away from what you guys do. We're creating a new internet. That sounds bold, but let me today give you a little bit of insight into what we're doing, what this SCION thing is, how we use it, how it can be used, what kind of use case it has. But let me first ask you, who here, with a show of hand, has heard about SCION? Oh, 4. I've expected less, so it's not too bad. Well, actually, Tim, yes. All right. Let me first maybe frame the problem a little bit or motivate why would we do something like creating a new internet, right? What's happening today is that the internet is becoming the backbone for critical infrastructure. I mean, it has to be the backbone for, video streaming, social media, all of that jazz for a long time. But also critical infrastructure more and more needs to adopt the internet. Things like, healthcare, electronic patient dossiers, or how doctors and hospitals exchange data or analyze cancer through cancer boards. The whole financial system, especially also with new fintech, open banking APIs, etc. This all moves to the internet. Today we have control of this distributed energy grid, a lot of IoT things, all being dependent on the internet. And some of these things you really don't want to be on the internet, right? The ones of you that work with networks, work with the internet, there's kind of a big risk out there, right? And this is just a claim that I make here. The internet is actually very outdated. Of course, it has been a big success story based on a pretty old protocol that no one ever believed will scale to the size it does today. So what are the problems, right? It's the internet itself that's maybe due to its own success is inherently very risky, right? Today, if you put something on the internet, it promises it connects everything with anyone, right? That's the promise of the internet. And that's fine for Google search, and that's fine for Instagram and all these big services. Now, do you want your electronic patient record being out there, exposed to potentially 18 billion devices, right? Of course, we build stuff, like we build firewalls, we build intrusion detection, we build all of these things. But fundamentally, if I put something on the internet, it's out there, right? It's on by default, and then we try to do blacklisting, which I believe, like, this attack surface is a big risk. Another thing with the internet is that you cannot control how your data travels through the network, right? And that might not matter for you if you browse Instagram, of course not. But it can matter a lot if you think about e-voting applications, or if you think about financial information that is quite often regulated, right? That needs to stay within a certain jurisdiction. We have a lot of laws that say, well, data at rest needs to stay within Switzerland, for example. And we have similar regulations that say, well, for these kind of applications, data can never leave Switzerland or the Swiss jurisdiction, right? That precludes basically the internet. On the internet, you choose your service provider, or maybe your two upstreams if you're your own BGPAS, and then you send off your traffic, and there it goes. You have absolutely no control, no guarantees. For one, nor do you have any insight, right? If something goes wrong, you don't know where things go wrong, because you don't know how the network looks like. Of course, you can use things like trace route and pings and whatnot to try and figure out what network path is being used. But it's all more a black magic, a voodoo, a black art than actual science. And because you're at the leisure of kind of the internet, and the internet is driven by economics incentives, your data quite often is actually also not sent over the best performing path, right? It's more like the cheapest path. Everybody is like handing off the traffic as quickly as possible because it's off your network, it doesn't cost me. So that quite often leads to very suboptimal routes. And none of this you can influence. And this is where we come in with SCION. So SCION itself is a new internet architecture. Technically, or you can think about it as a layer 3 protocol. It has a control plane, and I will talk about this, and it has a data plane. The control plane is roughly a replacement for BGP, or an alternative for BGP. And the data plane is basically how then packets get forwarded. So on the IP. So the SCION data plane is IP. The SCION control plane is BGP, like equivalence, right? Now, SCION has usually 3 pillars. That's what I usually how I introduce it. The most important of which is this notion of path control, right? What does that mean? That means I, as a sender of data, I get a selection of paths from the network, and I can make a choice. Which one do I want to use to send my data through the network, right? And that immediately opens up, of course, this use case of geo-fencing, right? I need to ensure that certain data never leaves a certain jurisdiction. So I will only choose paths that go through, let's say, Swiss networks, European networks, never cross Chinese networks, whatever it is, right? But it also lets me do other things, right? I have applications, if I do video conferencing or gaming or any kind of real-time application, I'm very interested in having a low latency and a very predictable jitter, right? If I do a large file transfer, or if I mirror my database to a backup site, I don't care about latency at all. All I want is throughput, right? And actually, the path that gives you the best throughput or the best bandwidth is often not the path that gives you the lowest latency. Now, if you have control over that, you can use the network in a much more optimal way, right? You can choose the low latency path for your video streaming or video conferencing, and the high throughput path, or even multiple high throughput paths together to increase bandwidth, right? So that's the path control from the perspective of a sender. Now, it always, to some of you that might be familiar with networking technologies, this sounds a bit like source routing, and we had that in the past, and it didn't scale, and why are you trying to do this? Because it's not fully source routing in the sense that the source I see the network and I can choose any possible path, right? It's different in a way that the network offers me a set of possible paths, and amongst them I can select one. But that also means, and that's a crucial bit, that me as, for example, a provider of a service, right? I'm usually the receiver. I can now control whom I make this service available on the network level, like who can see my service. If I want Tim to connect to my service, I give him path information. I make sure that the path information is available to Tim to reach me. If I want to keep out Sylvan, sorry, I just use you because I know your name now. I will simply not tell Sylvan about any path information that leads to me, and that's in my control because I'm the receiver, right? I can control who gets my path information, and then for Sylvan, my service doesn't even exist, right? I don't need to put up then a firewall because all of you can access it and keep you out and try to identify Tim and let him through and identify and kind of keep everybody else out, and then you have source IP spoofing, all kind of things. It's just a much cleaner way of expressing who can access my service or who can see my service on the network level. Of course, that's also great for availability because denial of service is a thing. Yeah, then there are 2 more aspects. The isolation domain, that's kind of a new aspect that groups together networks or autonomous system in kind of a common trust anchor or a common governance framework. So think of isolation domains as kind of like top-level domains, right? Every country would have roughly an isolation domain. That's how we envision it. And then you have purpose-built isolation domains, such as a banking isolation domain, maybe a defense or a Swiss defense isolation domain, and so on. And the nice thing about isolation domains is they provide network sovereignty. So to make all of this secure, there is, of course, there are certificates involved on the control plane. These are always rooted in some trust anchor, and that trust anchor is defined by the isolation domain. So I can say, good, Switzerland defines kind of a governance framework. I can be part of the Swiss isolation domain if I get the certificate, and the Swiss isolation domain can set up a governance. Okay, you need to be a Swiss business, for example, to be in there, or a Swiss resident to get something like this. In the banking world, you could say, well, you need a banking license, and you can build these kind of trusted isolation domains that are independent of others, and where also from the outside, nobody can revoke a certain key and then you're offline, which could totally happen, for example, today with RPKI or DNSSEC. Basically, the keys are controlled by organizations that are very close to the US, and they can totally disconnect entire parts of the internet. So that was very theoretical, still going to be a bit more theoretical, but on a high level, how this works. So what you see here are these 3 isolation domains, right? And in these isolation domains, you have SCION networks. We call them also autonomous systems, similar to how the internet is made up of autonomous systems. And then you have kind of each isolation domain has a core. These are usually the tier 1, tier 2 providers of a certain region, for example. And they are essentially here to provide connectivity, of course, within the isolation domain, but then also across these, right? And then you have on the control plane a pathfinding algorithm, or the control plane is there to define path segments or find path segments. There are 2 layers to this. One is intra-isolation domain, so path construction beacons, they flow from the core of the networks towards the edge, right, from L to O to S, and would collect path information. That's then a path segment that goes from L over O to S, or vice versa, right? This happens also in this isolation domain, and then you have the same happening between these isolation domains. So a SCION path then becomes a combination of 1, 2, or 3 path segments, right? In 3 path segments, you can reach any other connected place if the path is available to you, right? If this is, again, my example, I'm here, I can totally make these paths that lead to me not available to everybody, right? And then I'm also not visible to everybody. Nevertheless, then on the data plane, what you do is basically, if you're in F, you ask the network, hey, give me path segments that lead to S. And in F, of course, F doesn't know anything yet. It knows from this beaconing process that how it reaches A and B, right? So it asks A and B. A and B, they don't know about S, but they know that S is in this orange isolation domain, and they know from this part here how to get to this orange isolation domain. So they will ask K and L and M, and they know because S probably registers their path in the path registries here, right? And then, of course, you can cache this information. You don't need to do this on every packet or on every time you want to establish a connection. But you really put a form of these paths into the packet then, a reduced form. That's an overhead. That's what you have to pay for SCION connectivity, right? Each packet has roughly 80 bytes of overhead, depending on how long that path is. On the flip side, the routers that forward these packets, they're really simple. Because IP forwarding is, you look at the destination address, you then do a longest prefix match in a huge routing table, right? In an internet routing table, you have 2 million entries, and you need to do this, like to do this at line rate, you need to have specialized hardware, really expensive one. And here, the routing decision is encoded in the packet. So all a SCION router needs to do is actually look at this packet and then verify that this packet header here is correct. There's some symmetric cryptography involved there. It's basically an AES computation, which is very cheap, but it's the most expensive operation in SCION forwarding. It's very cheap compared to a longest prefix match in a huge routing table. It's independent of the network size, right? This stuff here will always be the same size. It doesn't depend on how many other routes are in there. And C, it's basically hardware accelerated on any commodity platform. So even on commodity server hardware, we can do hundreds of gigabits of forwarding of SCION traffic, right? So we can go quite far until we need to have custom silicon. And then, of course, all of this, so on the data plane, but also these path segments on the control plane, these are cryptographically secured. They give you the guarantee that once they have been created, they cannot be changed anymore. If I claims to be on that path, they're really on that path, right? Of course, that is always relative to some trust anchor. So much like the web PKI. So that has been very abstract. How do we use this today? This is where we come in. We're a spin-off of the ETH, and so far, all of that we have basically developed at ETH, right? And Anapaya was created to build the technology that this can actually be used in the real world, right? And the real world today looks like this. You have a backbone network, ISPs, Swisscom, Sunrise, British Telecom, Colt. They need to deploy SCION routers. Our product is called Core because it's at the core of the network, right? And think of these SCION routers, they're waypoints on a SCION path, right? A SCION path is a series of interfaces of this on these SCION routers. The more SCION routers you have in the network, the more diverse your network, the more operators you have, the more diverse your network, the more differentiated paths you have. But that's the cost. You need to have this backbone network that also creates and finds these paths, etc. Right? And then you have kind of the user side. The user can be individual users, but they can also be, kind of headquarters, virtual cloud deployments, branch offices, you name it. Now, none of these networks there at the edge or applications that run in here, they know anything about SCION, of course not. And requiring that we would upgrade applications or build SCION support into Linux or Mac or Windows would be, I mean, the proposition to attack the foundation of the internet is crazy enough, but if you would need to upgrade applications, you have lost from day one. So this is where the IP in SCION tunneling gateway comes in. We call this an edge. That's just our product name. Its main purpose is to take IP traffic, encapsulate it in SCION traffic, and based on a destination, then make a path decision to the other side where it gets decapsulated, right? So IP is found within SCION, so to the applications and the users of this network, this is completely transparent. Of course, that's the primary purpose. The secondary purpose is now also, this is the thing that makes the decisions of which path is the most optimal one, or that you configure with your security policies or whatnot, right? They come in different flavors. In the cloud, you can spin up a virtual machine and run this as a virtual router. Maybe in your headquarter DC, you have this as a physical appliance. Or then they also come as kind of carrier-grade version of this, right? Where Swisscom, for example, operates a bunch of these, such that these end users here, or these little IoT devices here, they don't need to run an entire IP and SCION tunneling gateway themselves, but they basically use the ones provided by the ISP, giving access to the SCION internet to all of these entities. And just to illustrate how this works, right? The IP and SCION tunneling, you have the sender there. It sends, in this case, a TCP IP stream. It could be an IPsec stream. It could be a UDP IP, quick, whatever. Just needs to be IPv4 or IPv6. It goes into that edge gateway here, right? The edge gateway looks at the destination address, and it, of course, it needs to have a routing table because essentially it's still dealing with IP traffic. It learns from other such edge gateways through a dynamic routing protocol what kind of prefixes they announce, right? So it figures out how the destination is now in this SCION network here, and at that point it knows where, on the SCION level, where it needs to go, right? And then it can make a path decision. And the path decision is always a combination of what path are even available to me. The paths that are available to me is dependent on the destination, but also on the core network in between, right? They all have a say in what paths are available. And then it makes a decision based on, okay, what kind of security policies I have configured and what kind of performance I know these paths have. And to give you a little bit more of an idea of how this can look like, we have a tool, a cloud orchestrator. It's called the console. And we have a demo version of it. This is the demo version, but the live version looks exactly the same. That's another powerful thing about SCION, right? You know all these paths, and based on these paths, you can actually graph the network, and you know which paths are being used to communicate to the other side. So you can visualize all of this. And now I didn't manage to mirror my screen, so bear with me as I find my cursor somewhere. Yay. Right, if I'm, for example, interested in my corp network, which is headquarters, Paris office, Ashburn office, I can look at this and see, okay, these are the different streams I have, some voice over IP traffic, some TCP traffic, right? If I click on any of these paths, I get insight, okay, these go from, you know, from the HQ to Cyberlink, and VTX and Swisscom, Switzerland to Swisscom, the US AS, and then to the Ashburn office, right? It's even payload is encrypted. We have this latency, throughput, etc. Right? We get this. Imagine getting this on the internet level, right? This is not a private network that we own, right? This is an internet, well, a SCION internet, and we can get this level of insight, right? So that's one thing. The other thing then is also how powerful it is to have to do traffic engineering. So if I for this I use now another domain. So here, for example, I have two kinds of traffic: sensitive, and we just label them sensitive and non-sensitive, right? And you can look at the sensitive traffic, and it has some path policy, and we can look at what the path policy is or how it's defined, but it like the name should suggest what the path policy expressed, right? It's Switzerland, and it should prefer the sunrise axis. And then the failover is just Swiss paths only, and the Swiss networks here are encoded in this light blue, right? You can see here, this is the Switzerland isolation domain. The European is the dark blue, and then the North American is the green one, right? And we have the non-sensitive, and here we send this over, you know, the Cyberlink axis here. So you see, we prefer this one. If that is not available, we fall back to the Switzerland only. But if that's not available, we're still okay with going through Europe, right? Whereas for the sensitive one, we said only Switzerland. If no Swiss path is available, well, then we don't send the traffic. Now, because this is a demo, we can, or a demo environment, by the way, you can play with this yourself. Just go to console-demo.anapaya.net. We can bring down links or ISPs. So for example, if I bring down this link here, then you see it failed over to this alternative path here, right? You can also bring down another one here, and it fails over to this one. It's, of course, you don't have to, now you think, yeah, this is a demo, that's how fast it goes. In reality, it also goes pretty much this fast, because you get immediate feedback when a link is down, and basically within one round trip time, you can fail over to another one. So it's not so far from the truth, this failover behavior.
Can I ask a question?
Sure.
Let's say those routes are down and you only have the sensitive traffic you want to route. Do you have to manually confirm an alternative route, or will it just say we're going to stop the traffic here?
Well, right now it would say we're going to stop the traffic, right? If now I have to be careful. If I bring down, oh, I still have a path then. Let's say bring down. Now I don't have any paths anymore. How can I force that there is here, right? Okay, so now the only path, it's a bit unfortunate that the color scheme changes because it uses determinism, like just the first one is blue and so on. You see, the only active one is still non-sensitive. It's the only, right now there is only a path that goes via Europe, right? And if I actually also kill the path via Europe and force it to go via the US, oh, I see. I played around with it, and there was already a US path filter in the demo. Never mind. I should have reloaded. Anyway, it would have stopped working, and what I wanted to show is actually if I change the path filter for Switzerland and in Europe, actually this is also pretty cool, right? You can define these path filters, and you can get a preview of the impact it has, right? So here, this is the path filter Switzerland and Europe between headquarters and in your destination here, and it shows you all the possible paths that or possible links that you might take, and you see the US one is grayed out, or yeah, redded out. So you basically get the preview of your path policy before you actually deploy it, and all of that, yeah, it's just based on having this path information available, right? If you have the Switzerland only, then you see the preview here. Well, it does not allow any of this these European or US networks. But anyway, you can then configure and apply a new path filter, and it would actually, you know, pick that up and route accordingly. And yeah. Oh no, it doesn't have a path. Okay, maybe the demo is broken. I just need to reload it, and then it flows again. This is front end only, so you cannot really break anything, right? Yeah, but it's also not very believable now that I had to reload. Anyway, you get the point. It's actually in production you wouldn't play around like this because you cannot kill stuff, but it's roughly how it looks, right? And just to give you an idea, what is possible with this technology on an internet level. Yeah, let me go back. So you might wonder what kind of use cases today are kind of addressed today. This was our first and still most prominent use case, kind of a multi-provider MPLS-like federated network, right? This is the Swiss Finance Network, Secure Swiss Finance Network. It connects today over 100 banks, nationally and internationally. It's called Secure Swiss Finance Network, but it has a lot of international players as well together, and they do all kinds of interbanking data exchange. The most prominent of which would be the Swiss interbank clearing. That clears up to 400 billion Swiss francs every day. If this one is down, you actually read it in the news. And this is since last summer, everything has migrated to a SCION-based network, right? And the reason for this was, or the use case was, before that it was kind of SIX at the center, and everybody had to have kind of a dark fiber or least line to SIX to have the star topology, but they could only use it to communicate with SIX, right? They could not use it to communicate, like there are a lot of banks that are service providers for other banks, or now fintechs are in there, right? They do a lot of interaction with other banks. So this is why also the internet gets adopted more and more, right? Because in these private networks, this any-to-any kind of communication is not possible. So they wanted something that allowed this any-to-any communication. They wanted something where they could control who is part of this network, right? And SCION and their isolation domains, they give you the key for that, right? So the Swiss National Bank and SIX as kind of the governance of this framework, of this isolation domain, sorry, they can control that only eligible entities enter this network by handing out certificates. You can only be part of an isolation domain if you have a certificate for that isolation domain. So if you control the CA, you control by extension who is part of it. Like even if Swisscom would try to connect a rogue bank from somewhere, they don't have a certificate from SIX, they wouldn't be part of this network. And they wanted this to be multi-provider, so no single provider lock-in, etc. So this is a primary use case, these multi-provider networks, kind of site-to-site connectivity. And we have a couple of others like this, but this is the biggest one, right? And it's very resilient and blah, blah, blah. Second use case, and this might be more interesting also for 9 or for hosters in general. It's basically providing a service and controlling where that service is exposed, right? And this is the gate infrastructure that we have built. So basically what you have here is you have your different sites. That could be your data center, right? And you have users, a set of users that need to connect to this. Today, this set of users could be, users in Switzerland, right? Because in Switzerland, we have 100% coverage through these IP in SCION gateways run by the providers here. And basically, if you have a service that should only be or primarily be accessed from users in Switzerland, you can make it available in the SCION internet and only hand out your paths to these gate providers, right? And it will be totally inaccessible from the internet. Basically reducing your attack surface from 18 billion devices down to 8 million people, let's say. We have done that a couple of times now. These are the numbers for medium-sized Swiss bank that moved their remote access to this SCION internet. Right? They said, okay, our employees work from Switzerland, so we need to guarantee the uptime for Switzerland. They had an internet-connected VPN access point and the SCION one, and they just compared, what do we get? You get a lot of scans. Nobody cares about those very much, but you also get almost 90,000 intrusion attempts, and these are, targeted attacks, as in try to use credentials that they phished somehow, try to send an attack payload that exploits some weakness that they have in their VPN solution or a service behind it. All of that basically went down to 0. Now, it doesn't need to be 0, right? The attacker can sit in Switzerland, and then you have maybe 1 or 2, but it's drastically reduced, right? It's not magic or a panacea that solves all your problems. It's just an attack surface reduction. Of course, there's the use case where you still need to be reachable also from the internet everywhere. And so what you do then is you expose yourself to the internet and to the SCION internet. And if you're under pressure, for example, a DDoS attack, you cut the internet leg, right? And if 95% of your customers are within this SCION protected area, then you would lose 5% of your business instead of 100%. So that might be interesting also for something like 9. But I'm not here to sell anything. I'm here to educate, of course. Maybe as a final bit, where we are in Switzerland. So this SCION thing is not just a theoretical idea anymore. I would say in Switzerland it has become a standard for critical infrastructure. We started in finance, right? That's still our biggest network. We have healthcare. This uses a lot this gate infrastructure, connecting more than 50,000 doctors to hospitals, to this health infonet, this kind of a healthcare infrastructure provider, centralized. And this is now all taken off the internet, like a national infrastructure taken off the internet into a sovereign Swiss network, but still accessible by all of you, right? We're working with the utilities. We deployed this year, and actually what just went live a couple of weeks ago is also retail payments. So this is now kind of an extension of this for all the merchants and all the payment terminals. We're working now on internationalization. We just landed in Benelux and France and Germany. This is ongoing, and we hope that we can replicate this, of course, also internationally. And yeah, I'm sorry, I'm slightly over time. I hope I could give you a brief overview of what this SCION bit is. Happy to take any questions. I'm also around afterwards. Yeah, thanks a lot. Yes.
So does that mean that ISP has to essentially provide SCION if you want to use it?
So the question was whether your ISP needs to provide SCION to use it. Ish. Let me say it this way. So for example, to cover the entirety of Switzerland, we have the big ones, Sunrise and Swisscom. They together have like 75–80% of the market share, right? they have native SCION available. And then there's a huge long tail of small ISPs. And for that, we basically run such gate infrastructure at the Swiss Internet Exchange and do direct peering with them, right? And make sure that basically extend our network to their network through filtering and BGP announcements and whatnot. It's a bit of a, it's not a hack, it's actually very clean, but it allows us to aggregate a lot of these small networks to still give them access to the SCION internet. Now, for you personally, the SCION internet is not yet very interesting because there's not a lot of content on it yet, right? If you have, if you of course have an electronic patient record that you would access via this HIM platform, then you would go through the SCION internet today, even if you don't know it. But generally, you're right. The cost of SCION is that we need the network operators to deploy these SCION routers. And that's also what makes it very challenging and very dragging to expand. Right? This is not an over-the-top internet solution. It's really something at the network level. It doesn't require new physical infrastructure, but it requires new networking, kind of logical networking infrastructure. And there we need the ISPs.
So thank you. If you have more questions, you can ask him afterwards.
Yes.
Thank you.
Thank you.